Welcome everyone to tonight's British Astronomical Association Hydrogen Line Group meeting, this 6th of April, Easter Monday, 2026. It's really wonderful to see you again, and I hope that you've had a good Easter weekend. I'm going to start by opening the floor this evening to Jason Burnfield, who, well, I'll leave him to tell us what he's going to talk about. Thank you very much, Jason.
All right. I'm going to start out.
Sorry, my apologies, Jason. Just to remind everybody, as usual, as I normally do, to remind everyone that this is a recorded meeting and will be available later on the BAA YouTube channel. Thank you very much.
Yep. Yeah. So I've built a new portable dish, a smaller one than what I'd previously had, I just completed it about a week ago, and I've been running it through its tests and doing some Milky Way scans, and I've actually got it in the middle of a second transit scan of M31 right now as we speak. In fact, it's still in the M31 is still transiting the beam at this point. It's 1.54 meters, so 154 centimeter diameter. I think detecting M31 will be pushing the limits, but I did do an analysis of a transit yesterday, my first one, and the results were inconclusive, but encouraging. And so I'm going to be excited to see what happens in the next 2 or 3 days worth of data gathering to see if I can see anything. One of the big steps up in my system from the previous setup is that I've gotten an AirSpy Mini as my SDR instead of my old new Elec Smart T, which is basically a slightly better version of the RTL SDR architecture. And the AirSpy has way more bandwidth. The pass band of the receiver is very flat, and so it makes it a lot easier to do the type of transit scans where I'm trying to capture these external galaxies, because the flatness of the pass band makes a big difference. And especially if you're trying to look at M31, the bandwidth, it makes a big difference, because M31 has a very wide spectrum because of the orientation, and so it's difficult to fit it in a bandwidth smaller than, say, 4 or 5 megahertz. And the AirSpy has a 6 megahertz bandwidth, which is awesome. So I'm really excited to see how that's going to work. What I'd like to do, I made a kind of a short video playlist on my YouTube channel documenting the build process, and it's fairly short. And so if it's all right with you guys, I was just going to go ahead and share my screen and play that for you. Let me see if I can do this here. Here. Okay. Screen. There we go.
Yeah, we can see your screen there, Jason.
Okay.
Excellent.
So I'm going to bring up the playlist for my mini dish build. See if I can just play it. Here we go.
I don't know, Jason, is there meant to be sound with it? Because if there is, I can't hear anything.
Oh, are you not hearing the sound?
I think what you need to do is when you do share, I think there might be an option. Let me just check. just have a look. If we do share, oh, that's right. When you press share your screen, there's a button at the top, on the top hand right of the share window, which says include sound. So you have to click that on before choosing the screen.
Includes. Oh, there we go. Okay. I'm also gonna mute my mic. So, I made a mini dish, a bit dish out of the scrap plywood left over from the large dish, and actually I've got all the pieces assembled, drilled, and ready to put it together. So I'll show it once it's assembled. So I got the mini dish all put together structurally. I still got to cover it. But yeah, it's set so that all the ribs are at the right height, and I've even put in the little nylon screws to set the ring height. And yeah, it's looking pretty good. Looking forward to covering it and then hooking it up and seeing how it performs. So I have stapled a nylon cord around the edge to space out each of the ribs at exactly the right spacing, and it holds it taut. So now it'll be ready for me to cover tomorrow with the aluminum window screening, and then we can hook it up to the feed and try to see if we can detect any radio waves. So I've begun covering my dish. Got 3 panels on, 2 more rolls of window screening, and I've figured out a method to keep them nice and smooth. So yeah, it's coming along pretty nicely. All right, I'm gonna show everybody how to set up my dish, how to unfold it. So, get out. Slide. Lean down until it hits the nylon screws, and then I put in the nylon pegs in place. And voila. And now, I've got my feed, which is just a cake pan with a loop wire. And then I bring that down and snap it into place where the notches are, and we're all done. We're ready to detect some hydrogen. So this is my setup. I have my ULX Smart T thermally bonded to a large heatsink, and I got it connected to the USB on my laptop, and then SDR Sharp with the IF average plug-in, and I'm showing a nice strong Milky Way signal. And if you look out the window, you can see the dish in the yard. There's my cable coming in through the window. So, hi everybody. I'm going to demonstrate how I take down and fold up my new mini dish. First of all, I take the feet off, and it just locks into place, held by those just by friction and fish. I have little nylon pins that I use to hold the ring in place. Take those out, and then I simply slide the ring up. Voila, it's folded up.
Wow.
So that's a quick little rundown of how my dish works. So the main design constraint was based on my experience when I first moved out here just over a year ago in January of 25. I'm in New Mexico in the desert now, and my previous dish was slightly larger, a little more flimsy structurally, and was covered with Faraday fabric, which is like a giant sail. And it was damaged very quickly by the wind. So this smaller, more robust design with window screening as the reflector material has already proven it can stand up to the wind a lot better. So yeah, it's sometimes the design of your dish has to do with your weather conditions in your locality as much as it does with its electrical properties. So anyway, I think what I'd like to do now is just do a live walkthrough and kind of show. So I have now switched to, I don't know if you can see that, I've switched to my new AirSpy Mini, which has way better performance than the R2L that I have. And I'm actually right in the middle of oh shoot. I still have YouTube playing here. Jeez. Okay.
No, it's okay, Jason. We can't see YouTube at the moment, but we are just on a screen that shows everybody's faces. You would probably need to enlarge your screen in some way.
Oh yeah, I gotta share my screen again here.
Yeah, so we can see your main desktop at the moment.
Okay, how can we? Is there a way to make? Let's see. Wonder if there's a way to make my.
Are you talking about making your camera enlarged on the screen?
Yeah.
Is that what you're saying? Well, I can do that for the video if I right-click on it, and everybody else might want to do this. If you right-click on Jason's picture and then left-click on Pin for me, that will bring Jason's picture up to full screen for you. But you will need to right-click it on it and unpin it again when he's finished.
So I don't know if you can see that. That's what I got coming in live from my AirSpy Mini receiver, and you can see the bump here off to this one side that's from the Milky Way, and the reason why I've got it clear over to one side is because I've got this centered to hopefully center the M31 spectrum within the flat part of the bandpass, and so that's what's going on. I've got.
Sorry, Jason. Can I just interrupt you a second there? For the sake of people who perhaps are new, I don't know if there's anybody new on this group today, but people watching the video might be new to this whole concept, and they may be a bit confused that when you're looking at a hydrogen line, you would expect the hydrogen always to be dead on 1,420. So why is it that sometimes it seems to either be the left or the right of the 1,420 megahertz line?
So there's two reasons for that. One is that if you're looking at different parts of if you're looking at hydrogen from different parts of the Milky Way, the hydrogen gas is moving with respect to us, and so there's Doppler shift involved that actually shifts the frequency up or down. But actually a lot of the Doppler shift is due to the orbital motion of the Earth as that vector changes direction throughout the year. It will actually move the spectrum that you're getting back and forth in frequency. It'll red shift it at one part of the year, and it'll blue shift it at the other part of the year, depending on which direction you're moving. So, and yeah, there's my dish. I don't know if you guys got a good view of that, with M Mountain in the background. So, and over here in the corner of my porch is the remains of my old dish, and also parts for a new build that will be. I'm planning to build one that's 3.5 meters in diameter, so it'll be a lot bigger. But right now I'm kind of focused on the 1.5 meter one and getting it working. So it's a lot more practical and easy to set up, take down. And later this month, as I guess most of you probably know, that I actually work for NRAO, and I work at the Very Large Array. And we're having our annual spring open house later on this month, and so that was one of my goals, was to get this small dish working well enough to bring it out there for the open house and actually do a live Milky Way hydrogen demo for the people that are coming, so they can just see it live there working. And the great thing is that this time of year, the Milky Way is high in the sky for most of the daytime hours, and so it makes it really easy to do a live demo all day during that open house. So I'm looking forward to that as well. So that's what I have as far as the dish goes. I know there was. I guess I'll kind of open it up for any questions or anything, and then I have a little treat for you at the end, where I recently got to travel to the Big Island of Hawaii to do some work at the VLBA site at Mauna Kea, and I have some video of that if you guys are interested in seeing that as well. So.
Well, that's brilliant. Thank you very much, Jason. Just before we started the meeting, you and I and Ted were talking a little bit about some discussions that had been on the SARA mailing list recently, where you'd put your initial attempt to try and detect a signal from M33 on the mailing list, and then had realised there were issues with that. And you were saying that you had great hopes for the AirSpy Mini. Do you mind if I ask you perhaps to tell us a little bit more about that attempt and what it was that led you to be concerned about what appeared first of all to be a good sample, and then also to tell us why you think the AirSpy Mini is a so much better possible option for sort of more, perhaps we should say, more difficult observations like that than something like the RTL SDR?
Yeah, so to answer the first question, the reason why I started to question that initial, what I thought was a detection of M33, there were kind of two reasons. One was, given the size of my dish and my experience with my larger dish and actually detecting it unambiguously back in 2024, I had some idea of what the size of the signal should be. And I was for a dish half the size, I would expect it to be no larger than 4 times smaller, right? Because it scales by the factor of a square, more or less. And the signal was way too large. So that made me question it. And then the other thing that I noticed was I realized that I had centered it perfectly in the bandpass of the receiver, and those cheaper RTL SDR type receivers, SDRs, have a very distinctive kind of bandpass shape that has a nice big hump in the center of the passband. And even though I was doing some processing techniques to remove most of that, because I'm using empty sky on either side of the galaxy as my reference to flatten the background, it still doesn't flatten it entirely. And what I discovered was, as I looked at some other observations that I'd done, they all had that same. I began to suspect it was just that kind of hump in the center due to the response of the receiver itself. And so if I didn't have the new AirSpy Mini receiver with the wider pass band and the flatter response, my strategy would be to purposely off-center the spectrum one way or the other by about 50 kilometers per second in Doppler shift, so that then if I saw it and it was off-centered by the right amount, I would have a lot more confidence that I was actually seeing what I thought I was seeing, right? Where if it's perfectly centered, there's this question, well, is it really what I think I'm seeing, or is it just, a symmetrical response of the receiver itself? So putting it slightly asymmetrical or slightly off the center of the passband really kind of would give me more confidence that if I did see something at the right place, that it was actually more likely what I thought I was seeing. But honestly, the biggest clue to me was that the signal strength was way too big. There was no way it was going to be that large for that small of a dish. And part of that comes from the experience of having done it multiple times with other dishes, with larger dishes, and kind of having an intuitive feel for the size of these signals. And there's some back of the napkin kind of calculations that I've been able to make too. Edward Mol is another one in our Sarah group who he's from the Netherlands, and he has also been doing similar types of drift scan observations of M31 and M32 using a 3-meter size dish, which is what I did. And we collaborated a little over a year ago in the spring of 25 for the Western Conference here on using the lab survey database from Bonn University, which was basically a survey of hydrogen around the sky, but mainly focused on the Milky Way. But we discovered that some of these brighter, closer external galaxies, that data is buried in that survey. And so if we treated the data sets that you could download from that survey the same way that we were treating our data from our observations, we could simulate what we should expect to see. And what we found is, it was a very good match, and it would give you a good idea of the relative signal strength you should expect based on the beam width that you chose to simulate from that database. And so we would, in fact, I did one simulation where I took a five beam width simulation, a 5-degree beam width simulation, a 7-degree beam width simulation, and a 10-degree beam width, and compared them, and you could see how the signal got smaller as the beam width got wider. And so it gave you some idea of how does it scale with the size, So I'd say the biggest advantage with the AirSpy Mini, it's like I said, it's about $100. I think it cost me about $180 rather than $50 for the RTL, right? But for that extra money, you get higher digital resolution. It has more bits for its A to D converter. It has a wider bandwidth, almost double the bandwidth, which gives you a lot more room to capture a larger spectrum. And the receiver quality is just at a higher level, to where the passband response of the receiver is more flat and even, and it tends to be more stable over long periods of time, which is very necessary for the types of long exposure drift scans that we're doing to try to tease these very tiny signals out of the background. Stability and flatness of response is a big help. Otherwise, you have to do a lot of tricks in post-processing to flatten the background, and then you're always questioning whether you're just making it show what you want it to show rather than showing what's actually there, right? So yeah, I'm definitely a believer in spending that little bit of extra money for the better receiver once you start getting into more advanced type projects like this. So now, as far as just doing observations of the Milky Way signal, the RTL SDR receivers work brilliantly for that. I mean, the signal is nice and strong, and for the money, it's definitely, that less expensive receiver really works well in that scenario. But when you start trying to get into more advanced observations, where you're trying to detect spectrums from some of these nearby galaxies that are 10 times farther away, or hundreds or thousands of times smaller than that, then you start seeing a big difference if you have a higher quality receiver. So
that's brilliant. Thanks very much. I suppose the one last question I would like to ask on behalf of the group here, and I'm sure on behalf of loads of people who will be watching these videos online, is when are you going to start selling these incredible foldable hydrogen line telescopes yourself as a business? Because I think you might well have a pile of people who are keen to buy them. And Pablo here, he'll stick it on a mount that will zip it around the sky, so you can select and follow whatever object you want.
Well, I would say probably that's likely to happen never. But on the other hand, I think the design, I don't have like a drawing package for this thing or anything, but I do have my design materials and somewhat of a description of it. So for those who would be interested in building their own, I could definitely, I designed my dish using a spreadsheet. I basically calculated XY coordinates to lay out on the plywood using a ruler and marking a grid, and I started out doing that, and then I thought, wait a minute, if I do this on cardboard and make myself a template, I can save myself a lot of trouble. And so I ended up making myself a cardboard template so I can quickly draw out and then what I did is I have a good friend in the local community who's a woodworker, and I just paid him some money to cut them out and sand them for me, because I was not so keen on doing that myself. My woodworking skills are not the greatest, so. But no, I was really pleased with how it came out, and seriously, all of the materials to build this literally came from the local building supply place. The only components of my system that you can't buy at the local building supply was the SDR, the LNA, and the SMA connector on my feed. Even the feed itself is literally a cake pan from Michael's. So it's an aluminum cake pan. And if you're interested in the design of that feed, which I've tried Kentenas, they work good. this feed performs pretty much identically to the Cantenna, but for me, it was way easier to build, and it's easier to work with. The design for that I got from Alex Pettit, if you're familiar with him, and he has some very detailed documentation on the exact dimensions and even where he can source the components from. So if you're interested in that, if you get on the Sarah email serve list, you could probably get that from him there. Otherwise, I think Andy or myself could probably find a link to that. So, because it's something that's been out there for a while. So that's a good thing about these groups is you get a lot of good collaboration, and some people come up with these brilliant ideas, and they can send you the plans, and that way you don't have to do all the work yourself, right? So
Brilliant. Thank you very much indeed. So if I could open the floor to any other questions or comments that anybody would like to make.
Hi, it's Mark here. Can I ask a couple of questions, Jensen?
sure.
Yeah. Sorry, I don't know where my video is. There, you can see me. Hi. Yeah. Sorry, I've just come back from the allotment, so I'm a bit mixed up. What diameter was that? Your umbrella dish?
It's 154 centimeters, 1.54 meters.
And that gives you a beam width of.
I think theoretically you could get down to somewhere less than 11 degrees, but practically speaking, especially the foldable design is not ideal. It's not a perfect surface, so I lose some there. But my guess would be that I'm somewhere between 11 and 12 degrees in beam width on that. So
another question: did you use this famous Noelec sawbird?
yes. In fact,
And
that's the LNA that I've always used. I just recently purchased a new one, and it's they've updated their design. The case is a little bigger, and it has a different DC power connector. I think it's got a USB-C now rather than whatever they had on it before. But I power mine through a bias T most of the time anyway. So, but yes, it works brilliantly. And for the money, it's about $40 or $50. So
yeah. So you power the sawbird via not via the coax. Is it got its own?
I've done it both ways. So one of my Noelec radios SDRs does not have bias T built in. So I was able to just use a DC block with a USB-C cable to power it. But then my other two SDRs, my AirSpy Mini and my Noelec Smart T, both have a bias T DC power built in to into the input connector on the SDR. So in both, and I find that that's a lot simpler if I can do that. It's just less hardware to have to deal with, right? So.
And the coax, is it very? I mean, I went for that LMR 400. Is it very important that length of coax?
No. Once you have that LNA, it boosting your signal up, about 40 dB. You can stand to have some loss in your cable. My cable is about 25 feet long, and I have about 6 dB of loss at the L band frequency, and it works fine. So
okay.
now
Sorry,
you do want to make sure that you got cable that's rated to up to the at least 1.5 to 2 gigahertz.
Yeah.
But
Sorry, last question. And what oh God, what was I going to ask? Oh yeah, what software are you using to record?
I'm just using the AirSpy's SDR Sharp with the IF averaging plugin, which is what a lot of us are using that. And I find for doing the types of doing the data capture that I need to do the to try to detect these like M31, M33, those kind of things. I find that capture, the IF average gives me the best performance as far as the most samples per second, which matters, as you know, when you're trying to detect these very small signals. Time on target is paramount. The more time you get for each transit scan, the more you suppress the more your signal to noise ratio gets better. And so having more samples per second, or as much as you can, is pretty helpful. I found with my 3-meter dish that I needed at least an hour of integration time to see anything useful as far as these smaller signals from these external galaxies. Because we're talking 1 or 2 thousandths of a dB above background. So we're talking very, very small.
Then you're tracking your object.
No, I'm using drift scanning. So if I was tracking, I wouldn't be so worried about the sample rate, because I could just stay on it as long as I want, right? And I'd have plenty of time. But when I'm drift scanning, I'm pretty much locked into a limited amount of time based on my beam width and the rotation rate of the Earth. So, so I get with my 12 degree or 11.5 degree beam, M31 stays in the beam for about an hour, a little over an hour, which is a long time, but yeah.
Oh, great! Thank you very much. You've got a very good location there in the desert, huh? No RFI.
Yeah, it's pretty decent.
Thanks, Jason. Thank you very much.
Yep.
Yeah, Pablo has to leave us soon, so perhaps he should give us an update before he has to take off.
Yeah, that would seem very very reasonable. So first of all, thanks very much, Jason, for a wonderful presentation. I think that's very exciting. So just pass the floor over to Pablo now. Nice to see you tonight, Pablo.
Okay, I only have 7 minutes because I got to go to the dentist. I have a massive toothache.
Oh, you poor soul.
I
hope it's not the stress of trying to do radio astronomy that's caused it.
Possibly. It's possibly the fact that I was abducted, but they didn't probe me because they only like me as a friend. So let me share what I'm doing really fast, because I have 3 projects. I'm thinking about doing a Zoom, because one of them, it's going to take a long time, and that will involve Ted Klein's Ezra as well.
Would you like to... sorry, Pablo, I mean, by all means present whatever you like to this evening, but would you like to be our main presenter at the next Hydrogen Line meeting?
Well, I don't know if the main one, but I do have about an hour of material. But let me show you this video here. Also share tab audio. Okay. Chrome tab. Yeah, this is it. Some of you have seen this video. This is one of the projects that I'm working on. Can you see it?
Yes, we can see your discovery dish there.
The discovery dish.
already mounted on the IXS 100. That's about $229. That's $299. The dovetail I printed with PETG at 100% infill, and it's super solid. And I used the same hardware that came with this dish in reverse to attach it to the dovetail right here. A couple of weights that I had, and it's balanced perfectly well. And as you can see, it looks good. Of course, this is just a technical part of it, the structural part of it. And now I'm going to attach it to a PC. But right now I can use this program with the iPad. So I can say, okay, let's go to the Andromeda Galaxy, salute to the object, go to, and there you go. Okay, so it's perfectly balanced, and it's perfectly suitable for the Discovery dish, or even something heavier. So now I have a means of tracking. Of course, I'm going to add the Alex Pettit fence around this eventually. But right now, I can point and track, and my next job is to do the electronics and connect radio eyes to it. But it should work. Also, I have another dish, and I'm thinking about having two in tandem, perhaps, to add a little more surface. But right now, even at 27-degree beam width, this should be okay. It's tracking perfectly well, no problems. So now I'm going to go ahead and park it. I go to settings, park. Okay, I'm going to stop sharing here for a second because I really have to leave in a couple of minutes. So obviously I got to get the Wi-Fi situation taken care of. So I got some. I have two ways of doing it. I have a copper foil that I'm going to build a Faraday cage around it, and I'm in contact with Explore Scientific to try to deactivate the Wi-Fi because it can actually drive this mount, $299 mount, via a serial cable. So I'm going to be able to do that in the next couple of days after they do something to my tooth. Another thing that I've been working on is, actually Andrew has done some poetry about it, which I appreciate it. I created a song, so we're very creative people, but I've been working with AI and trying to corroborate everything that I'm doing with the scientific world. And it's so far, I've created a lot of material with AI out of my 2.1 meter dish. And I've been learning a lot, and there's a lot of, and one of the things that AI is asking me to do is to use ESRA to check the scientific portion of it. So I need to work with Ted because it's not exclusive. It's actually, they complement each other. And with AI, which by the way, SETI's using AI right now to look into hidden signals from the SETI at home, because there are terabytes of, and we're going to be creating terabytes of data that needs to be analyzed, graphed, explained, and used scientifically. So that's what I'm trying to do with AI. With the Discovery dish, if I'm able to actually successfully finish that, we're going to have something better than the scope in a box. I was going to show you a lot more. Can you guys hear me?
Yes, we can hear you. Yeah. Any questions from anyone? There is one question I would like to ask Pablo, which is not meant to be a challenge at all. It's just to ask you what you're hoping to be able to do with a small dish that you can direct in this way that perhaps you wouldn't be able to have done with a drift scan.
Well, you're going to be able to actually stack. You're going to be able to stack more, get a better SNR on certain, even though admittedly the beam width is going to be like 20 some degrees. You will be able to stack for better SNR, maybe able to detect certain portions of the sky, better mapping. It's a 70 centimeter, but it's just also a way to develop a system where I can eventually put a 1.54 meter antenna, and so it's a proof of concept and a way for me to waste time and forget about life. So with that, thank you so much for your time, and great meeting, and I gotta go.
Thank you very much indeed, Pablo. Thank you, and I hope you're feeling a lot better soon, very soon. Brilliant, fantastic to Pablo as well. So, right, one other discussion that started just before the meeting started this evening, which seemed to me such an important, covering so many important aspects, was one we started having with Francesco. So I asked him to hold off, and we would discuss it more within the meeting itself. Now, we've been lucky enough to be following Francesco here as he's been showing us his own process for making a radio dish with this wonderful 3D printed dish that he's got. So I'm sure you'll be able to give us an update on that now, won't you, Francesco? And then we're having a discussion about the effect of the blockage from the feed as well, and perhaps we could reprise that one as well, if you don't mind, as well, after you've told us how your dish is getting on.
Yes, Andrew. First of all, let me make a consideration. I see on YouTube, I saw all of this 2 or 3 days ago. I already see on YouTube, and meet these friends in this evening is incredible. I see the people who made these footages. Okay, I practically finished the surface of my antenna, and I attempted to expand it. Let me show my project. Do you see it?
Not yet.
Oh no.
So sorry, not yet. We can't see anything.
Sorry.
It's the share button at the top next to the leave button. Ah, hang on. Yeah, brilliant. Your desktop has just appeared.
Oh, this one.
Yeah, fantastic.
This has 3 steps. At the beginning, I thought to make it a completely full surface, but the time of printing with my Russia printers were too much longer. So I decided to divide in empty hexagons. So I arrived to this solution. Sorry, this is only a sector, one of 6 sectors of my dish. Every hexagon is different from each other. So, but I must repeat this bunch 6 times. The feeder is offend.
Sorry, Francesco. Did you say that each hexagon was different from the other hexagons?
Yes, this is different from this one, because of the curve of the parabola. This is, you see, this wall is different from this one. This is more angulated than this one.
Oh, very interesting.
But if I repeat this bunch 6 times, I have the complete surface. Returning to the feeder. The feeder is at the end of this PVC pipe. The focal distance is 720 centimeters, and the diameter is 120 centimeters. The FT ratio is 0.6. It's not too deep for a radioastronomy dish. But if I eliminate these pieces, 1, 2, 3, 4 pieces, I could increase the size to 180 centimeters. The FT ratio is 0.4, and ideal for to be illuminated from a patch antenna. Maintaining this red of the smaller dish and adding this blue, I could increase the dimension. But as you can see, it's a job, extenuating job. For every hexagons need to about 4 to 5 hours to print. So I must before I check how it goes to the smaller dish, and eventually I expand it. So I took about 3 weeks to print, and about 4 pieces a day, and I haven't a print farm. It should be speeder. It should be quicker. Sorry. So I will publish on Thingiverse as a free project. So this is all. Finished. I want to ask something to Jason. Sorry. Do you think that if the receiver has a very stable oscillator, do you think that I have some advantages? To have a VFO controlled by a GPS discipline and oscillator.
So you're talking about a receiver that has a frequency, stabilizer maybe, using
Yes.
GPS?
Yes.
That would be important for something that is pulsing like a pulsar, but if you're just measuring Well, I suppose if you're just measuring the intensity to plot the galaxy on the sky, I'm not sure it's important when the signal gets to you. But if you are going to plot the galactic arms, then I suppose a stable frequency is important. I'm not sure that it requires a frequency stabilizer, much like GPS. So for pulsars, yes.
Actually, if you actually think about it, pulsars are still fairly wide bandwidth, and so really your actual advantage would be the case if you're looking at something maybe like masers, which are a narrow band type signal, where you really need the frequency accuracy. With hydrogen, it's fairly broad sort of peaks. Pulsars are also fairly wide bandwidths. So the real advantage of a very accurate frequency would be that if you were actually looking at also a narrow frequency emission, something akin to masers, which are much more of a fine frequency, and that's where your advantage would be. Pulsar, what you actually need is better timing, so you can accurately detect the individual pulses, the timing of the pulses.
Yeah, well, yeah, the trick with pulsars is when you're trying to detect them with a small dish, the way I understand it is they take advantage of the fact that they have a very precisely known period, and so you can kind of cheat if you know what the period is to a high degree of precision, and you have a high degree of precision timing on your data collection and timestamps on your data. You can actually do something called period folding.
Yeah, you can fold
where
it.
you can basically stack up periods on top of each other and get a lot more SNR.
Yeah, but the problem with a pulsar is that the signals are quite weak. So with a small dish, you got no chance.
Yes, because I have an AirSpy R2, which has an external input for reference frequency.
Mm. I have found anything we're doing, I think even the maser work that Edward and Dimitri have been doing, I think didn't require any more accuracy than the onboard crystal control oscillator.
Edward has an internal reference from a Leo Bodmer frequency that he can actually then adjust for the spike. So see, if you had an accurate local oscillator, you wouldn't need that. So he's actually using a reference signal from a GPS stabilized source that he can then adjust his actual received signal to. So if you had a very accurate frequency determinant with a local oscillator that was disciplined, then you wouldn't need that.
Yeah. But honestly, for hydrogen line work, I mean,
you don't need it.
The tenths of parts per million of the onboard is plenty of accuracy.
Absolutely. That's
the other thing is when we're look even though hydrogen is an emission spectrum, it's generally spectrally broadened by Doppler shift. So really, and usually the FFT bin resolution that you're using is, plus or minus a few tens of kilometers per second. So I mean that translates to, you don't need super accurate clock. What comes on board is plenty of accuracy to do hydrogen line observing. So I find that when I do VLSR correction for my external galaxy hydrogen line observations, I only type in the VLSR correction to units of accuracy. I don't even go to tenths because there's no need. It's in the noise as far as, my bins are much wider than that. So.
Okay.
I'm question in that regard, if I may interject. Would having the crystal oscillator temperature controlled better, would that help? And if you put something like a Peltier device over where the oscillator is to further chill it, would that help?
Yeah.
You really don't need those kind of accuracies unless you're really looking at a narrow bandwidth signal. That's really
Yeah, and
a very small bandwidth.
Yeah,
In my
and what I
experience,
found.
LTA device and anything, you get a big ball of ice around the bit that you're trying to cool. It kind of overdoes it. But the RTL dongles with the metal cases and the SMAs on, they have generally have a 0.5 parts per million TCXO, which is more.
Yeah.
That's good enough.
Yeah.
That's good enough.
I've got the Pluto. They've got an external 40 megahertz clock you can bring in, or any of those Pluto clones from AliExpress. They're perfectly good, and they give you a really good external reference. Again, using a Leo Dobner or similar, if you need that frequency precision on your receiver.
Yeah, the same thing with RSP receivers. They have an external clock input that you can stabilize. But again, for this kind of work, you really don't need it. You really don't need that kind of accuracy. You just don't need it. The cooling, if you want to cool your amplifier using like liquid nitrogen, that might help your signal to noise ratio. Okay, so that's the only place where you might actually get some advantage by any kind of cooling, and that's for the LNA front stage. By cooling it down, but you need to go way down.
Yeah.
You know, I mean, that's why some of those receivers that are really low temperature used to use like liquid helium to cool the front end.
Well, all the ones that BLA do, they have cryogenic.
Yeah, see, so exactly. So that really gets you very low noise in your front end amplifier. But if you're just doing anything like cooling with a Peltier or something, what? Okay, so you get to minus 10 degrees. That's not gonna do you much good at all.
Yeah, where
Always goes up.
our
Outside,
temperature
there's a big
control.
ball. Sorry. Yeah, you get a big ball of. If you're not careful.
Yeah, where I find, so the reason I have a big heat sink on my SDR is not so much to control to stabilize the frequency of the clock, but is to, what I found is when I'm doing long duration drift scans and stacking multiple days of drift scans to try to detect these very small signals, the stability of the receiver bandpass shape changes ever so slightly, and if you can keep the temperature really stable, it doesn't matter where it is as long as it stays the same, right? And so keeping it very stable helps to reduce the amount of drift that I get in the shape of my passband. Which, when you look at it from the perspective of the levels we're looking at when we're doing Milky Way galactic hydrogen, the changes are almost invisible. I mean, it's very stable, but when you start zooming into thousandths of a dB above background, you start seeing significant movement over long periods of time, and so that stabilization helps. It doesn't eliminate it, but it reduces it some. It makes it a little bit easier to get a nice smooth data curve that then you can use either a first order or second order background correction to flatten it, and then it's good. So.
There was something else that we were discussing earlier, which I think is perhaps worth revisiting, Francesco, and that was that you were asking the question whether the size of the feed, such as the size of a cantenna, can meaningfully affect the function of the radio dish. Jason, would you like to comment on that? So see what you, because you mentioned something, or I mentioned it really, and you seconded it at the time, but maybe you do a
Well,
better
yeah,
job than
so,
me
I mean,
describing it, really.
the back of the napkin calculation is, comparing the square of one area to the square of, it's one area to the other. So the square of the radius, the ratio of the square of the radius of the obstruction versus the dish. And what you find is, like the example was a 15 centimeter obstruction with a 120 centimeter dish. And what you find is you get just under 1.5 degrees, or just over 1.5% of difference, which is pretty small. And so, I mean, you that wouldn't start mattering until you've eliminated a lot of other areas of loss. What I found when I first started trying to build a dish and was testing out my early prototypes is something that Alex Pettit brought out with those small Wi-Fi dishes is one of the problems you have with relatively long focal ratio, like 0.4 or 0.5 or so, is that because we're not putting our dishes up on a high tower somewhere, they're sitting on the ground, or they're relatively close to the ground. Ground spillover is a big problem. And I noticed, so one of the things I started doing was, when I design dishes, I try to keep my focal ratio in the 0.36 to 0.27 range, which is a lot more shallow. But what that does is it shields you from ground spillover. And when we're looking at signals in the sky that are, tenths of a Kelvin, 300 kelvins just swamps that. The ground noise is just, it really affects your performance in a big way. So shallow focal ratios are really good, especially for smaller dishes, I've found. The cool thing is, if you have a moderate focal ratio on a moderate sized dish, then if you want to make it bigger, you can just add more stuff and you still have plenty of room. You can reduce your focal ratio and you still have plenty of room. You can use the same parabola and just extend the sides, right? So, but yeah, the ones that I've used successfully to detect M31 and M33 have had focal ratios in the neighborhood of 0.31, 0.36, something like that. So, and they were all in the realm of around around 3 meters or just under 3 meters. So, yeah, pushing it down almost half the size to this 1.54 meter, that'll be a big test to see if are we getting to the limits of what's possible. So if I can successfully capture the blue shifted peak of M31 with this small dish, I'm going to be ecstatically happy. I'm going to be, because that's not been done before. I don't think anybody's used that small of a dish to detect something that small. So, but I don't know. We'll see over the next few days of data collection whether I'm getting anywhere or whether it's a lost cause. So,
so you would
don't know if you don't try, right?
Yeah.
Jason, question for you: If you track M33 and accumulate a lot of signal, do you think it's helpful for detecting M33?
Well, yeah, definitely. If I could track it, then I could collect a lot more signal, a lot more integration time in a shorter overall period of time. My setup is purposely low tech, so I'm setting my as-L, tying my dish down, and then drift scanning for days at a time. So I'm collecting lots of integration time, but I have to be very patient. I have to wait for, an hour a day or 45 minutes a day, depending on the declination of the source, right? But over time, when you start stacking 4 or 5 days worth of data on top of each other, you start to see a noticeable difference. And it's kind of interesting too, because when you learn a bit about the theoretical mathematics behind, the radio astronomy, I guess they call it the radio astronomy equation, right? The noise drops as 1 over n squared, the number of samples that you gather. So if you look at it 4 times as long, the noise is half as big. If you look 9 times as long, it's 3 times as big. So
root square of n. 1 over root square of n.
yeah, exactly. Yeah. So you have if you want to reduce your if you want to increase your SNR by 3 times, you have to integrate 9 times as long. So it's all about patience. Of course, there's a limit to that. I mean, obviously there's a limit to that, but I've stacked 5 or 6 days worth of observations, and I could definitely see each day the noise dropping. So.
Thank you.
Jason, I had a question. You mentioned a little bit earlier about the DC spike on your Mini, and so I'm curious. I think it's even worse with the RTL SDR. When you were doing your M31, M33 scans earlier, even with a bigger dish, how did you avoid the DC spike problem?
Well, actually, I never really had trouble with the DC spike. What I had trouble with was just on the RTL SDR, I had trouble with the fact that the passband response of the receiver was moving enough. It was changing over time, ever so slightly. And so as I integrated long periods of time and multiple days of observations, sometimes I would end up with a background that was just so curved that I couldn't flatten it with a nice, simple function. Because usually, even on professional observations, like when I use the 20-meter scope at Green Bank to do galaxy observations, using the same method where I do on-off. That, for those unfamiliar, what you do is you take on-target data and then you subtract slightly off-target data from it. And what it does is it flattens the background and it suppresses the Milky Way signal, because the Milky Way signal is basically the same in those 2 spots. But what I found was that the passband response curve of the SDR was changing enough that when I got done doing my data analysis, my spectrum was, I would have to use like a 3rd or 4th order fit to flatten the background. And what I found with the AirSpy Mini is it's way flatter and way more stable. And so what I'm finding is just the few times that observations that I've done so far, once I do my off-target subtraction, it's almost completely flat. I mean, I had a very, very gradual 2nd order curve to it. I probably could have flattened it even with a linear fit and it would have been fine. It's just, the performance is so much better. But yeah, I did find, I got one Newelec SDR, a cheaper one, that it wasn't a Smart T, it was something else, and it had this horrible DC spike in the center. And I think it's just a cheap one that didn't have balanced INQ. I think that's what was happening, and there was no way to get rid of it. It was just it was unusable.
But the DC spike is basically a mixer response. That's if you use direct sampling receivers. If it goes to a 0 IF direct sampling, then what that is just a local oscillator. You're
Mhm.
seeing, because it's at 0 frequency, so you're seeing the
Yeah.
local oscillator bleed through the mixer. So with other receivers, we're actually doing a almost like a heterodyne type IF shift
Yeah.
to a frequency other than 0, then that you don't see the DC spike.
Yeah.
So that's what that problem is. So so you're seeing the ARC2 Mini has, so you're seeing that problem now. And I think AirSpy.
I've only seen it on one receiver, and I don't use that one. So I haven't seen it on the New Alex Smart T, even the RTL SDR, the cheapest one that I used, didn't have that part. And I think it's because, like you said, it's using heterodyning and it's upshifted. It's not at DCs. It's not baseband.
Yeah.
So
Yeah, well, that's about the only way to really get rid of it, unless you do sort of the digital, which doesn't work quite as well. Okay, thanks a lot. Appreciate it.
yeah, like I said, my biggest challenge with the external galaxy observations is the stability of the receiver passband shape. And like I said, the AirSpy Mini is so much better. I mean, it's just, I don't think I can ever go back to an RTL anymore, because the AirSpy Mini is just so much better. And it was a little more expensive, but it wasn't that much more expensive. I mean, for what you get, it's definitely worth the money.
Yeah, but I agree. Your passband is going to be much more affected by the temperatures. So your heat sinking and maintaining it. It doesn't matter what the temperature is. You just want to keep it the same for all the observations. So yeah, that's the way to do it. Yeah. Okay, great. Thanks a lot. Appreciate it.
Yeah, and then of course, if you want to have a super stable temperature for really, really inexpensive and simple, just take that big huge heat sink and set it in a bucket of ice water that's stabilized at the freezing point, and there you go. I mean, that'll be rock solid, you know.
Well, that's one way to do it, as long as you don't submerge your SDR, and then that'll kind of ruin your day, wouldn't it?
Yeah, that would not be fun. Just got to make sure the tray is shallow enough, right? So.
Well, you do the early astrophotography thing, digital astrophotography thing. You have a heat sink that you can pump the coolant through it.
Oh yeah, that would be one way to do it.
Yeah, and that way your electronics is out of the water and you're cooling off the heat sink as you go.
Yeah.
Okay.
Jason, Dave Bracey here. I've got a quick question for you. You said you're using SDR Sharp with if averaging, integrating over roughly about an hour. Do you have plans to? And I think you said you also have plans to stack multiple days together.
Mm-hmm.
So, what do you use to do the stacking?
I tend to be very unsophisticated in my methods. Edward has written some nice, nifty little Python code to suck in all those text files and do all the math. Mine's very labor intensive. I just basically pull them all into an Excel spreadsheet and do all the math in Excel. It's simple, but it's just labor intensive. It takes a while. But I think the reason why I went that route is because my overriding design principle for the whole project is I wanted to make my methods and my materials accessible to people who aren't technical, so somebody who's doesn't have a background in programming, they don't have access to all this fancy hardware or fancy stuff, and they can just go to the hardware store, buy everything they need, build the dish, and then they can dump the files into Excel. And it's tedious. It takes some time, but it's also, I find that it also makes it easier to see what's going on, because there's no magic behind the curtain. It's just, you're literally just, it's very simple and very straightforward, I guess.
Yeah. Yeah. Okay, that's fantastic. That's really encouraging, actually, and I like that approach. That's really interesting. Thank you very much.
Yeah, and the other thing is the plotting tools in Excel are pretty capable for doing the kinds of plotting that we need to do for this kind of observation. I mean, I'll have a sheet for my raw data, which is basically just columns of frequencies and amplitudes, like raw digital amplitudes, and then I'll have an analysis sheet where I pull in the frequencies and I convert them to LSR corrected velocities. And so I'll have a cell up there where I can go on to Greenbank's VLSR correction page and type in the coordinates and the date, and it'll tell me what the VLSR correction is. And that way I can correct for the orbital motion of the Earth and remove that from my data so that I can compare it directly then with published survey data, and it won't be off, right? That was one of the first things I discovered when I first started doing radio astronomy in the backyard and just looking at the Milky Way. You know, as soon as I found the lab survey database and I started downloading those spectral profiles and then looking and comparing my data, I was like, why is the frequency off? You know, and then I thought, well, maybe my cheap SDR has maybe the oscillator's drifting. But then I looked at the specs and it was, a TCTO that's temperature controlled oscillator that's a half a part per million accuracy. So I was like, okay, that can't be it. But then I started to notice that the frequency error was systematic as I went to higher and higher galactic longitudes, it increased. And then when I went around the other side, it started decreasing. And I was like, what would cause that? And it was like I accidentally discovered what VLSR correction was. I didn't know that because I'd never done anything with radio astronomy before. And then I went down the whole rabbit hole of looking it up and learning about it and what it is and why they correct for it. And it was a whole learning process, by tripping over it, and asking the question, why is this? So to me, that's the greatest thing about this amateur, getting to this as an amateur, is there's things we don't know, and we don't know, and we find out by tripping over it and then asking the question, why is this wrong? Why is this off? The shape's right, but the frequency's wrong. What's going on here? And then when you discover what's going on, you've learned something in a way more impactful way than if you just read it in a book, So
yeah,
that's what I find. That's what I think is so neat about this, is you're actually doing the stuff yourself. You're building the hardware yourself. You're doing the data analysis. That's why I like doing my data analysis in Excel, because it's like hands-on. It's very, you're directly involved with what you're doing.
Okay.
So anyway,
yeah, completely agree. Thank you very much, Jason. Appreciate it.
Yeah, we were talking about the cooling. I don't know if you guys can see something like this. So this is you can pick these guys up on, I don't know, eBay or whatever. So you can attach this to your SDR, and then you have these ports where you can run your coolant liquid through it, and then just attach this to your SDR, and you can run your ice water or antifreeze or whatever you want to run through it, and so that'll do the job. You don't have to immerse your heat sink or have a huge heat sink on your SDR.
So what's that called, Adrian?
It's just basically a liquid cooled heat sink.
Liquid cooled heat, and the idea would be to connect like a gaming coolant system, would it?
Yeah. So see the ports here you can just attach the tubing on the ends here. One, I think they're both equivalent. One would be your input, the other one is the flow through, and then of course the surface area you can just attach. This is actually used for peltiers. You can stack peltiers on here for pulling out the. Well, you could do it both ways. You could use the peltiers to cool this, but these are usually used to pull the heat out of the peltier, because usually you need a really large heat sink to get the heat output from the thermoelectric coolers, and so so you stack your thermoelectric coolers on here, and then keep them cool through the liquid circulating through the ports here, and you can pick that piece cheap. I have a couple of them here that I've been wanting to use for some other projects, but anyway, so this is one option. If you just don't want a huge, massive heat sink, or of course, then you have to have the problem of a pump. You need a pump to circulate your coolant, and you know, probably water would just work, or you can use antifreeze and then maybe get it down to a lower temperature if you'd like to do that. Anyway, I just thought I'd like to show you. You can pick these up eBay. This is where I got these guys from. I'm sorry I don't have the exact site for it or whatever. I can maybe look it up later or something. But so you can get these sort of things that'll do the job without having to use massive heat sinks, and they'll do the trick. Anyway, I just thought I'd point it out so you guys will be aware of it.
Yeah, so I've just looked up on eBay, and they're called aluminium CPU radiator water cooling block liquid water cooling heat
they're
sink.
also used for CPUs for people that like to overclock or for gaming and stuff. Yeah, use it for that also.
And sometimes for they're called a memory cooler as well.
Yeah.
Okay. Brilliant.
Anyway, so that's an option you can use.
I think that was an absolutely stunning discussion that we've had for the last hour or so. Thank you very much again, Jason, Francesco, and everybody else that's taken part. I'm very much aware that other people have not had a chance to speak. So who needs to rush off quickly and wants to say something more urgently? Oh, nobody. In that case, what I'll do is I'll go to Michelle, because you're located east of me and therefore are running later than the rest of us.
It's okay. It's only 1 hour. I am not in eastern part or wherever. No, I don't have much to say. I just I have a question for Ted. I wanted to know if EasyCall is compatible with their Spy Mini, because so far I used the New Lake RTR, but I'm not sure that I can use their Spy Mini with EasyCall.
You're going into uncharted waters. I call you a pioneer. Andy has been there, a couple other folks, and so it's possible in two methods. One is using SOAPy drivers, which know how to talk to different hardware, including the AirSpy Mini. And then we can get into the wild world of GNU Radio, where we've been doing experiments as well. And that also uses SOAPy drivers to talk to lots of different kinds of hardware. So yeah, we can talk by email.
Okay, if you can send me the information, I'm ready to try.
All right. Good luck.
You have my email?
Yes, I'll come after you.
Okay.
Yeah, but
so nothing really.
I'm interested in it too. I own iSpy and I want to use with Ezra.
Okay, but you haven't even really begun. Beware what you're getting into. It may be simpler with an RTL SDR, the simpler and cheaper SDR.
Yeah. After my personal experience,
but you are a brave fellow making your own dishes. So yeah, we can give it a try.
Thank you.
I've got to second what Ted has just said there. I think for most people, starting with an RTL SDR makes a lot of sense. Although I'm very much aware in this group we have many people who are much more knowledgeable about electronics and radios than I am. So I'm talking about myself really. It certainly made sense to me. But my Etus clone, Ted got working for me using SOAPy drivers.
Maybe I have a question for Jason. You speak about the ground noise with a small antenna. I have a Wi-Fi. I have a Wi-Fi antenna. If I put some layer of grid on the my antenna is mounted on a pillar, and it's on a terrace platform. If I put some metallic grid underneath, does it help to avoid the noise.
It might. I know Alex Pettit did some experiments several years ago where he just extended the sides of the dish, not to make it larger, but just to shield the ground noise, and it greatly reduced it moved the noise floor visibly down. Like you could definitely see an improvement immediately. And I found that also to be the case. On one of my early dishes, I just had some dowels that were attached to window screening, and they would slide into these little PVC pipe fittings, and it would add an extra 7 or 8 inches of shielding to extend the edge of my dish a little bit farther. And it wasn't a smooth parabolic surface, it was just to shield from ground noise, and it made a noticeable difference. But then, but then of course the next time I designed a dish, I just made it have a shorter focal ratio, and it got rid of that problem. So.
Okay.
I know that Alex has pointed out it's one of the most useful things that most people can do, and that it does not matter whether the extension is parabolic or not.
Yeah, and it makes a big difference. It's like the easiest thing you can do that will add extra performance pretty quickly and cheaply. But the other thing is it's easy to try it and see what happens, and then report back and tell us what you find.
I will try.
Okay, brilliant. Well, thank you, Michelle. Is there anything else that you wanted to discuss, Michelle?
No, it's okay.
Brilliant, thank you. So, who shall I choose next? Mark, how are you getting on? Are you managing to solve your issues with interference, or is that still the bane of your existence?
Sorry, my camera. I'm concentrating more on this solar radio astronomy at the moment. I'll go back to the hydrogen later. I'm trying to set up this super SID observation system, so maybe this is not the right forum to talk about that.
No, but we have got a meeting coming up in the next week or two, which will be the right forum, so please come and tell us about it there.
Yeah. Okay, thanks guys, very interesting evening, thank you.
Okay, fantastic. So Tom, have we still got Tom online? Yep, brilliant.
Not much to report. I'm still learning Ezra, getting better at it. I'm plowing through all the instructions and everything. My little dish is mounted up on a roof, so once it's up there, there's no way I can move it without clambering up on a ladder, which my partner says, no, you will not do that. So she who must be obeyed. But no, I've been doing pretty good with recording data and everything like that. And I'm interested in learning more how to stack radio signals. I haven't seen how you do that in Ezra yet, but I would be interested in learning more about that technique. I'm getting lots of data files, and I would dearly love to know what all I can do with them.
So you got these signals that come down from the sky. If you do a drift scan long enough, you repeat the same point in the sky, and the program Easy Sky will start integrating the different data for these different points in the sky. So that's where they get combined. If you want to start playing with the radio signals, there's been a recent edition where I will integrate and combine signals according to their frequency and right ascension. And so that looks like a lot like a EasyCon 87 plot except the x-axis is not time or sample number. Now it's right ascension. So those are two ways to integrate. Usually we worry about the easy sky, and it glues them together for you pretty painlessly.
Okay, so that's multiple files then, though. I would have to.
Yeah, only because Ezra cuts it once a day.
Right. Okay.
As far as I'm concerned, it could be one big long file, but yeah.
Yeah. Okay. All right. Yeah, I haven't tried that yet, so thank you.
Brilliant.
I think it's in the demonstration PDF, so have a look in the docs directly.
Yeah.
I walk through that. Good luck.
Okay. Yep. Thank you.
So next, I've got a message online from Richard. I presume, Richard, this means that there's nothing more that you would like to particularly discuss. If that's wrong, please just say so now. Okay. So next person on my list, then we've got Ted. Ted, anything you would like to tell us about and how you're getting on, etc.?
Yeah, you guys are all talking about this radio astronomy stuff. Okay, well, that's nice. But Andy,
sorry, I must apologise there. I suddenly realised we've got two Teds online. So sorry to Ted P and Ted C. So yeah, carry on, Ted C.
So the other Ted, please.
Oh, okay, we're going to go with Ted Barton. Oh, okay.
I'm building a horn antenna which looks like something in the dissecting lab.
You don't have any pictures as yet?
I'll get one for the next meeting. Yeah, I should do some part-way pictures, but it's half built.
Oh, I'd be very excited to see those because it's something I'm hoping to build soon, a horn antenna. So I'd be interested to see how far you've got and learn a bit about your experiences and particularly any issues that you're having that are making it more difficult. So I need to be aware of those and how you're managing to solve them, or if you're managing to solve them. Okay, but thanks, Ted. So Ted C then, Ted Klein. Sorry, Ted.
I've lost my connection here. Let's see. I gotta go find the directory and click on this. Okay. Now I think I'm equipped, and what we need to do is now share that with you folks. Hang on. Pushing buttons. Share. Window. And finally here. Okay, Andy wanted to know about the weather. He's always looking behind my ears here, and it's blue sky and looking pretty. But since I have retired, I find that I'm even busier now working for this public observatory. And up on that roof, we have a little camera that's looking straight up in the sky. It has a fisheye lens, and so it's an all-sky camera. When you look up on top of the roof, it's like lying on your back with your feet to the west. And this was the weather when we started the meeting. I simply took a snapshot of it. This is available on the public web in case you want to know what my weather is. I am so lazy, I often look at this instead of opening the windows. So, okay. We can see the ecliptic in red going across here, and sure enough, over here behind the clouds is the sun. A little next to it is Venus and a whole bunch of other things. In fact, if you click on this, you get a whole planetarium out of this software, and it tells you where things are. There's the sun in yellow, and a whole bunch of planets nearby that we can't see during the day. Lots of constellations. It's just kind of amazing what you get with the free software. So yeah, you could build yourself an all-sky camera. Today is cloudy, but let's go to a night that was kind of clear. This is gluing all the images together throughout the night, and we get star trails, of course. And if you look closely, there are even little dots going across here. Some bright star leaving one image at a time. Off to the right is where the North Pole Polaris is, and we can see that it traced about half a circle. So we got something like 12 hours worth of darkness that night. A pretty good night. And we see planes coming along in straight lines with lots of blinky lights. This might be a little meteor over here on the right, another meteor up here, so that's nice. But this color camera is great to pick up the aurora borealis as well. We can see its color because at some time that night we were up in the dome, turning the dome around, and you got to see the red lights on the inside down here on the bottom left. So that's gluing all the pictures together. But let's change things entirely and talk about another camera to tell you about the weather. I have 4 cameras looking out at 90 degrees from each other, looking up at the sky. This is more recent. And these cameras are sensitive enough to see meteors at night. If indeed we plot their coverage on the sky, it actually covers up a whole bunch of the U.S. Let's see, should I do this? Yeah. We can see the 4 petals showing the coverage of these 4 meteor cameras. I just think this is kind of fun. Wouldn't it be fun to have other cameras also see that meteor up in the sky, and therefore we can start, I guess, triangulating, figuring out where that meteor physically is precisely in time. So that's what this program is all about. No meteor should be unviewed. Okay, now let's see. Let me go to the next one. Wow, if we look at one of them, this is looking north, and the sky can get busy if you have that much sensitivity. We can see airplanes flying all over the place with lots of blinky lights. But in the background, you can see lots of arcs. And again, way up here in the middle, there's a little bitty arc showing Polaris, but there are other lines on here. The computer studies all these pictures every morning, and before it reports to the global database up in near Toronto, Canada, it removes a lot of that information. And it gets it down to this. All those airplanes kind of have been removed from the image. Here's Polaris doing something like 12 hours worth of collecting. An airplane or so will sneak in here because it just wasn't removed. But wow, we see all kinds of meteors now. Maybe satellites, it's hard to know at this point. We can see some of the star trails, but not as much as before. Cool. Well, indeed, every night it also studies where those meteors were in the sky. This is showing the whole sky, right ascension declination. And it found a lot of little lines up here at the top. We are way over here in March on this calendar of the whole year. And over in March, there's like not really any meteor showers. But let's go to a different date, like back in August previously. And wow, there were lots of meteors coming out of the sky on the same kind of camera. And when you plot that on the full sky, we see all kinds of little lines. And if you trace where they came from, they seem to come from one radiant for the Perseids in green. There's another radiant that night, NOA. I see PAU down here in pink. And so it is noticing all these radiants for these different meteor showers. And if we look down here on the calendar on the bottom, this red line indicates when that was taken in August. And there are a whole bunch of meteor showers that should be active. So that's kind of fun. All this is documented to one degree or another on our webpage at the observatory. There you can see it up on the top, and I'll even put it in the chat. I hope that's kind of fun. Go check it out. I wrote up a bunch of PDFs about this. Questions? Yes, not.
That's quite that's quite brilliant again. Thank you very much, Ted. I I know it's not hydrogen line, but it is interesting to see how people are extending the work that they're doing, particularly when it comes to providing a outreach to the communities.
It has been distracting me. Yeah.
Quick question, Ted. With your color cameras, can you discern different colors from different meteors, and maybe perhaps think about their composition, and maybe to classify the different types of meteors? I'm just wondering.
Not with my camera, no. And of course, I don't know where the meteors are coming, so I can't zoom in much closer. You're asking a lot, so we're doing spectroscopy in your question.
Well,
we can't do that, but we could study where they are and what time they happen, and get a better count for the meteor showers and how many per hour.
Yeah, I wouldn't even go as far as spectroscopy, but some meteors have a distinctive like green colors or blue colors or reddish colors, and that can give you some clues as to, are they stony meteors or carbonaceous chondrites or whichever. That's kind of what I was referring to. If you could maybe at least get a rough idea as what type of meteors you're talking about.
Not with the cameras I can afford.
Okay, well, just wondering. I think that'd be kind of cool also if you could get that extra data. But anyway, that's cool. That's really neat stuff. Thank you.
It's worth saying that the BAA has the last couple of years been running a new beacon based at Sutton and Mansfield Astronomy Society near Nottingham in the UK, and that's sending out a signal at around about 50 megahertz, and that and part of the advantage of that frequency is that it does improve your ability to do effectively spectroscopy of the signals that you get back. I mean, on my radio meteor setup, I'm doing mine at 143.050, which is Graves in France, but that's picks up more meteors than the BAA beacon, but it is less effective for trying to ascertain the sort of features that you're talking about. So that's the sort of research that they're hoping to be able to do. And the other thing they're doing is they are starting to erect a number of sensors which are produced in exactly the same way, because that's one of the other problems with meteor observing, that people are not using exactly the same equipment. So what's detected by one system is not the same as what's detected by somebody else's system. So they're trying to get a database of, as the way that Ted's describing it, of detections at different parts of the country and maybe in different parts of Europe, where they can then tell where a meteor comes from and its track, but also be able to determine its features from its spectrum, its radio spectrum.
I'm sorry, Andrew. I'm a bit perplexed. You used the word spectroscopy using the radio reflection. Are you referring to Doppler?
Well, yes, I suppose so. Yeah. Well, I mean, yeah, I'm being a bit sloppy in the terminology that I'm using, really. But they're able to determine the radio spectrum. You're right. It is separated in terms of Doppler shift, but also there comes the question of where that Doppler shift comes from, and trying to ascertain those sort of features as well, and as well as directional features from the data. But you're perfectly right. It's not a proper spectrum of the meteor at all. It's a radio meteor scatter.
Yeah, right. Okay, thanks. I was just kind of confused on that.
No. I was being sloppy. Sorry about that. Okay, moving on to the next person, Dave. Is there anything that you would like to talk about tonight?
Andy, yeah, sure. So I think in the last meeting I mentioned that I was thinking about going over to 10-bit Ezra and using multi-day integrations that Ezra offers. But
sorry, Dave. Sorry to interrupt, Dave. For the sake of anyone who didn't hear the last meeting, the discussion there, can you perhaps just remind people what you mean when you say 10-bit Ezra?
Oh, okay. Yeah, sure. So I've been using Ezra for, a while, not a while, but a few months, and I completed a map, I suppose, of the most of what I can see from here in England. But I wanted to think, well, how can I improve it? And so I tried out a few features, and I tried multi-day, keeping fixed on one declination for multiple days and allowing Ezra to integrate and seeing what improvements I got. And I did find improvements. And there was also Ezra also offers a feature to, I think it defaults to 8-bit logging, but you can change that to 10-bit. And I tried that as well, and I saw quite a considerable improvement doing that. So, and I also expanded the diameter of my dish a little bit. And so put all those three together and thought, yeah, I've got quite an improvement here. But the only problem is that 10-bit and 8-bit I don't think are compatible. So although I've got a lot of 8-bit and a lot of 8-bit data, I want to go to 10-bit. Means I've got to start again. So yeah, that's what I've done. I've started again.
Is that true, Ted? Can Dave combine EZB and MPZ files in Ezra that are taken with different bits, or are they completely separate from each other?
I probably assume that you're not changing your mind so much. So yeah, you got to pick one. Otherwise, it gets complicated. How would I merge 1,000 readings onto 256? I am working to allow different frequencies, like a different center frequency, so that Jason can glue different galactic velocities together. But I haven't done sizes, freak bin quantity differences. So I think tough luck.
Yeah, that's fair enough, Ted, and that's what I thought. So
Yeah,
never mind.
there's technically a way to do it, but it would be really complicated. You'd have to do a bunch of math processing on the data to make it, to basically interpolate in between to give you sort of artificial data points for the lower resolution ones or something.
Well, I haven't, to be honest with you, I haven't minded though, actually, because as the months have gone on, I've learned more, and I've improved my techniques, and it's been a good opportunity actually to start again, clean sheet of paper, and work my way through. My only problem is that I've got to deal with my wife, where I'm allowed to have the kit out for 10 days, and then I have to pack it away for 10 days, as we sort of share the space. So which slows me down a little bit. But there we go. That's life, isn't it? But yeah, so that's what I'm up to. I'm remapping, and I'm let's see, I'm 22.5 degrees through now, going at 2.5 degree increments, and I'm going to go from, let's see, I'm going to get up to get 90 degrees done, so I'm about a quarter way through.
If you had one of those wonderful foldable dishes that Jason has just made, that could just fold out every evening when you guys went to bed, and then put it away.
Well, I'm doing 24-hour scans. But yeah, that would be good, wouldn't it? Yeah, and of course that allows me to do a bit of maintenance in between as well, and all that sort of stuff. So it's all good. I don't mind. So yeah, there we go. That's what I've been up to.
Oh, brilliant. Okay, Bob, is there anything you'd like to talk to us about?
Yes, I'm a true beginner, and I have built Alex's disk Yagi, and I've been starting out with SDR sharp and IF average, and as far as I got so far has been looking at the sorry about that. at the cold sky and the hot earth. And now I'm trying to understand how to set the variables for the 2.8 IF average to do like a 3-minute scan or a 5-minute scan. And I've been searching online, and I asked Alex, and he sent me a couple things to look at, but I still don't understand how to within SDR Sharp and IF average 2.8 on how to set up the system to do like a 3-minute integration time or a 5-minute integration time based on the variables listed.
What I've found is I think it can vary a lot depending on your setup, but I just do it experimentally. I set it, and it'll count, and then it'll reset. And what I'll do is I'll set it up to do multi-save, which automatically saves a file every time the count resets.
And which count is that?
So
which variable is setting the count?
It's let me open it.
That's good.
I'm sorry I don't have it open in front of me because I'm on a different computer.
Yeah. Give me a second. I'll open up I'll open it up so I can see, because I can't remember what it's called.
Do you want to share your screen, Jason, so we can all see the program?
Well, unfortunately, I'm on the call on my work laptop.
All right. Okay. Fair enough.
So I don't have it on that, but I've got my.
You're saying, Jason, it varies simply because of the speed of the PC that you happen to have?
I'm not entirely sure. I think it ideally it's just the settings on the SDR, but I've found that it does vary slightly. Like one of the things that I try to do to make it stable is I put my laptop in airplane mode and shut off all the external stuff when I'm doing data capture, and I try to not have anything else running in the background as much as possible so that I don't get interruptions in things taking clock time. But I think it does. I don't think there's any way to completely get rid of background interruptions and stuff. But what I found is, so there's a slider called dynamic averaging, and so the three things that kind of set your how many how often you're saving files. One is the FFT resolution, which is how many bins is it separating the data into frequency wise, and then there's an intermediate average, and I have mine set to 1,000. And all that really does is sets what the range on the dynamic averaging slider will give you access to. But for instance, I have my dynamic averaging count set to 8,559. So 8,559,000 counts, and that gives me roughly 5 minutes of integration time between each file capture. It's not exact, but it's roughly more or less 5 minutes between each count. But what I would suggest you do is set your bins to, say, your FFT resolution to 128. That's probably a good place to start. Set your intermediate average to 1,000. And then turn your slider on your dynamic average down to almost to maybe just one step above the lowest, which is like 451,000 counts. And that for me, that gives me like 3 or 4 seconds between each one, something like, or 5 seconds, something like that. And then just kind of increase it, and what you'll see is it'll increase the amount of time in between each. And I just kind of do it experimentally. I let it run for a bit, and I find, okay, this count gives me about this amount in between each. And I find that once you set it and you let it run for a bit and capture some files, you can look at the timestamps on the files, and they'll be pretty constant once it kind of stabilizes. And so, yeah, I would suggest kind of experimenting with it and finding out what works in your system, and just like keep increasing it and watching the count between the files until you find you're where you want to be, and then basically write that down in your notebook or whatever. I have a notebook that I use for my observation planning, and I write down stuff like my ASL settings, because I'm doing drift scans, and my VLSR correction for that night, my center frequency and all that stuff. And then, so you could write down, okay, what dynamic averaging count am I going to use to get, 5 minutes in between each capture, in between each data file. So yeah, that would be my advice, is just kind of experiment with it and see what your system does.
Okay, thank you. Do you, I can save like maybe 20, 25 files like you're saying, just to see if they're all showing up at that roughly the same time, and then do an increment and see what happens again, and just keep doing it until you get somewhere in the 3 to 5 minute range.
Yeah, that's what I would do. And you're going to get close pretty quickly. So, I mean, once you watch 2 or 3 of them you can tell whether they're constant or not. So, they don't vary that much. So like, I would give it 2 or 3 samples and look at the times and see if they're kind of stabilized to a pretty much a constant value. And then you can kind of use that as a guide to say, okay, that gave me 2 minutes. Now if I take that count divided by 2 minutes, it gives me counts per minute. And then I can, calculate from that, okay, if I want 5 minutes, how many counts do I need? And it'll get you close. It's not going to be exact, but you get as close as you can, basically, to what your goal is,
Yeah, thank you.
Yep.
That was it. That was my question for now. And once I learn that, I'm sure I'll have another one.
Oh, no, brilliant. Thank you very much, guys. Yes. So the next person, we've got John. John, anything you'd like to talk about?
I'll just unmute myself. Sorry for the camera wobble earlier, but my phone was running out of charge. I could only find one short USB cable that would I could prop the phone up. So I do apologise for that. Not much astronomy going on here, but plenty of outreach. This time last week, we're at a school at Canterbury, just by London, UK, organising a contact with the space station, coordinated out of Houston. Absolutely wicked. We've got 2 of the kids in the school got their radio licenses, so one of them started to contact, one of them closed the contact, and there were 17 kids in between able to ask a question and get the answer back from Jack Hathaway, I think he was a test pilot, now astronaut. So that was really good. Absolute hook into the kids, into the science, all of it. We had ham TV running, so a similar sized dish to the one we saw earlier. Sorry, I forget who it was who was showing that. About a 1 meter dish, running a 2.4 gigahertz receive system for the ham TV downlink. Trying to sneak in between the 4G mobile phones coming down and the Wi-Fi coming up. There's a sweet spot just in the middle, which sadly in Ireland now I don't think actually exists because 4G has been extended. But it worked a treat. As soon as we about 2 or 3 minutes into the contact, even on such a small dish, we're able to get good solid video onto the big projector screen in the school hall. So lots of very excited school children, very hooked into the science and the ongoing legacy of the radio club in the school. So that's absolutely brilliant. That's what I've been busy doing in the last couple of weeks. But not much astronomy, but plenty of outreach and plenty of space radio. So yeah.
Yeah, well, that's fantastic. Fantastic. Thank you for telling us about it. Okay.
Yeah, it's a lot of fun.
And also on my list, I've got Adrian. Before you speak, Adrian, is there anybody else that I have missed? No, I think about everyone. So, Adrian, the floor is all yours, sir. Anything you'd like to talk about?
Oh gosh, I think I've already said probably way too much today.
No, not at all, not at all.
But I would like to, since actually John just opened it up, so I feel like I don't have to break the continuity here. But I would like to ask Ted. Now, Ted is a member of another organization that some of you might be aware of, and that's DSCS, the Deep Space Exploration Society. And they have a really, really, really neat, interesting project that they're supposedly trying to do right now, which is trying to detect the signal from Artemis 2, which today will be going around the backside of the moon. And I think that's super exciting. So it's kind of perpendicular here to radio astronomy. But Ted, you're a member of DSCS and probably been there for almost since the inception. Could you give us a little bit of an update as to what's been going on with DSCS and the Artemis 2 project?
Oh my gosh, I was supposed to stay awake in those meetings? Oh gosh. Deep Space Exploration Society has the advantage of a club, a private club that controls a dish that's 60 feet across. So that's a heck of a radio astronomy dish. It is so big, and we can control it well enough, we think, that we are approved at one of 60 or one of 30 from NASA to actually be on the short list and get the real details so that we can track it as well. I'm not sure we can understand any of the signals coming down, but we might be able to at least make sure that it's still beeping and where it is and such like that. So they're working on that, but I'm not involved. It's 4 hours away from me in Colorado, so I can't. I'm just not up to date. Adrian, there is a Groups.io forum for DSCS, and so I would think that would have the latest news, and so have a look there. But they may be kind of busy right now. When I look at the NASA YouTube that's live, they are about the same distance from the Earth as the center of the moon. So they're working their way around the back end of it. And I think in about 2 hours, they are actually going to go behind the moon, and we're going to lose radio contact, for 20 minutes. So this is the exciting stuff that's going on. And it's progressing well enough. I don't see any people shouting, and so it all looks good. Does that help?
Yeah, I actually, I get the group IO news feeds, and so I've had a little bit of a update from them, and saw that they put one out late yesterday evening.
So I'll try to find that and post it here in the chat. I think everybody can read it. I think you have to be maybe an approved member to be able to write to it. So anyway, but you could read the newspapers.
Yeah, I think they've had a little bit of a problem. It's been a little bit spotty with some of the signals they've been able to receive. Again, I think the main, as you said, they can't decode the actual signal. That's encrypted, obviously, by NASA. But the main goal, as I understand it, is the NASA wanted to get very accurate Doppler shift data from their transmission carriers, so that they could then analyze all of that together and project out accurate trajectories and so forth for the mission. So that was the main goal from getting these sort of you could call it citizen science deep space network type of assembly that they picked out those individual approved sites. So that's really fascinating. I know here in San Diego, a couple of ham radio operators that have significantly large dishes, 10 meters and so forth, that were approved. And so, yeah, that's progressing. I think it's really exciting. We were talking earlier about frequency stabilized oscillators. Here's one place where you would definitely need a very, very accurate local oscillator and frequency determination in order to be able to present any of that Doppler shift data that NASA would be interested in acquiring from individuals. But anyway, just...
Well, what I read is that the telemetry is not cryptography. It's open I mean, the coding is open source, so you can get the telemetry. It's the frequency also is published. It's 2.283 megahertz.
Well,
Gigahertz.
that was one of the
PLS.
frequencies. Actually, 2.2165, I believe, is the main,
yes,
one of the main
that's
frequencies.
correct.
Yeah, and so I don't believe that the encoding is open source.
No,
because
it's what I read is that what I read is you can decode. It's not. I understand it's not crypt. You can. I don't have the source. I don't have a code, but I understand that you can. I mean, you can decode. It's not something very special.
Okay, well, if you can do that, more power to you. My understanding is that that's.
I don't have the antenna to do.
Yeah, because a lot of their voice communications and so forth can include some private messages and so forth. So I find it difficult to believe that they would allow.
Telemetry, I mean, just the telemetry signal.
Okay. Well, anyway, the main criteria again was the Doppler shift on their signal. That's the main thing that NASA wanted. So I just thought I'd bring that up. And there's a whole group of other people out there that I guess this is sort of parallel to radio astronomy, but people that monitor different space probes, some of the Mars orbital spacecraft, some of the probes that are going out to Jupiter and asteroids and whatnot. And there's a whole group of people that monitor those type of signals. So it has a lot of similarities to what radio astronomy does, except that they're not natural signals. But anyway, I just think that's interesting. And since that was brought up, I just thought I'd mention it again. Something really exciting going on right now. So Andrew, that's pretty much my my sort of non-radio astronomy contribution for the meeting. I would like to ask, could you give us a little bit of an update on your stuff? I saw the picture of your really nice feed that you placed on your solar cooker. How's that coming along? And have you gotten any data out of it? I'd be really interested to hear about that.
Really?
Before you go there, John, you were trying to show us something. What was all that?
Yeah, go for it.
Right, you don't need a big dish. You do not need anything more than about 6 or 8 feet.
Wow.
So what I've got here, a military low noise amplifier, 8.4 gigahertz. The deep space band is just above that, and this is plenty broadband enough to pick that up. Then there's a block down converter. This brings it out on a nice IF that you can then feed into an SDR Play or, hell, even an RTL dongle. And with a 6-foot dish, we managed to watch the probe going through the rings of Saturn, and you could see the signal Dopplering, so you knew you were following the right signal, and then you could see it dropping out as it passed through Saturn's rings, and then obviously disappeared on the other side as they impacted on the planet. But you don't need a massive dish to follow this stuff. Mars Reconnaissance Orbiter's the same. They're all in the 8.41 gigahertz deep space band. I mean, it's nice to have a 60-foot dish like Coon Hilly 6 or one of those others, but you can actually pick up the data. Well, pick up the signal, not decode the data. And as you say, it's the high bandwidth stuff has got, in the case of the Artemis mission, has got personal messaging on it, so you won't be able to get that. But you can follow it. You can get the Doppler from it. You can track it. You can see them go on the far side of the moon. You know when they get comms blackout. You can see their signal coming back, and you can learn a lot from it. It's a lot of fun. You just need a very understanding wife to have these things in your back garden. But what I have got is a couple of smaller domed dishes from an ex-Navy kit, military SATCOM kit, because it shares the same band practically, because it's an RF quiet spot. It's why they choose it. So 8.41 gigahertz. The 2 gigahertz frequency you mentioned is used by a lot of satellites as well. That's the SGLS channel block, and virtually every satellite, certainly in low Earth orbit, and all the geo stuff, will have that on board. Not as a primary comms channel, but it'll be there in case of, I don't know, say a geostationary got a bit of a wobble. They'll switch to commanding via SGLS and picking up sort of telemetry from that, because the beam width of the antenna is so much wider. If the spacecraft is tumbling, you've got more time on target with your tracking and your telemetry and command and control. But yeah, there's plenty of stuff up there, and you've already got half the system. You've got the laptops, you've got the LNAs, you've got the dongles, you've got the dishes. You just need to modify a satellite TV LNB perhaps for 8.4 gigahertz, or find some ex-military kit on eBay, and yeah, happy hunting.
Well, maybe not the LNAs, but definitely the rest of the gear's almost there.
But LNAs are easy. I went to the Friedrichshafen ham radio rally some years ago in Germany on Lake Constance. And there's an Italian lad there, I can't remember his name now, but he's been selling this stuff for years. He was selling the PCBs from dual satellite LNBs. And, obviously, with any of this surface mount stuff, you can read the layout of the circuit board like a schematic. So all you do is go at it with a pair of decent stout scissors, well, shears nearly, and cut out from the circuit board the amplifier stages and mixes that you want, tab them down, glue them down to a bit of substrate, and then just wire in the DC as you need, put an SMA on the ends of it, and away you go. It's not that difficult. People overthink it and think this high frequency stuff is hard. It really isn't. It really isn't. So much can be achieved just by having a go.
That's apparently the X band, 8.4 gigahertz.
Yeah, that's right. Correct. So it's number 15 waveguide or similar. Number 16 will work, which is normally the sort of 10 gigahertz amateur band stuff. Normally it's number 15. Obviously coaxes don't really work. But remarkably, rummaging around on his desk, got to be some here somewhere. Can't find it for other stuff except in the 1A. Keep picking up what I thought was the right thing, but it's not. That's a 50 caliber rifle cartridge case. But no, the 22 millimeter plumbing pipe, the sort of stuff you buy from any hardware store, 22 millimeter copper water pipe, is a perfect waveguide for working at X band. And then you get a LNB from your satellite dish, cut the horn off the front, pare that down to 22 millimeters, and then you can sleeve your copper pipe onto that, and that becomes the first stage of a receive system. It really is not rocket science, so to speak. This one's more optimized for GeoSatellite Oscar 100 amateur, operating on 10.4 gigahertz. But with some small modifications, these will work down to 8.4, or the parts within them. So yeah, it's not entirely impossible to knock it up on a dirty workbench in the back of the garage and strap it to a dish in the garden and get results. It's really quite achievable. Oh, there we go. That's the pipe I was looking for. So copper water pipe, LNB. There you go, and that's the feed system. It says for Burton. But yeah, all quite achievable. There we go. One I made earlier.
Eat your heart out, Blue Peter.
Oh yes.
The Americans won't know what I'm talking about.
me some sticky back plastic in here somewhere.
Well, thank you very much for that. Amazing what you get at the end of these meetings. I don't know if anybody's got any thoughts. Okay. Well, thank you very much for everybody for contributing to tonight's meeting. It's certainly been, I think it's been fantastic. The next meeting will be on the 4th of May at 8 p.m. British Summer Time, which is 7 p.m. UTC. And so I hope to see you all then. Thank you very much. Bye for now.